Hey guys, so I decided to record a video for the last two practice problems of the in-class problems for Unit 7. So get those out, you should have them out, and we're looking at pages 6 and 7, numbers 9 and 10. All right, so let's look at number 9. So we have this reaction, H2O plus Cl2O forming 2HOCl, and we're told the equilibrium constant K at 291 Kelvin is 0.090. And then we're given a whole bunch of information about different aspects of this reaction. Now, the one thing that I want to point out is since the K is less than 1, let me make my highlighter a little bit bigger. Since the K is less than 1, that means that the reaction is driving back towards the left, that the reactant side is favored, and that we can also predict that the delta G will be positive. Okay, so remember, thinking about what your answer is going to be and what sign it's going to have, stuff like that, that is a good way to know if you've done the problem correctly or not. Okay, so we're going to find, for part A, we want to find delta G of reaction using only the information given up here. So we could do, or you might think, oh, let's do the going home to supper equation, the delta G equals delta H minus T delta S. We can't use that though because we don't know the delta S of the reaction. The only entropy information we're given is about our two reactants. We don't know the information to find it for the whole thing. We are given delta H of reaction, but not delta S of reaction. And if you look ahead, we're going to be calculating delta S of reaction later. Okay? So going home to supper equation is not going to work. We also cannot do products minus reactants for delta G because we don't have, the only thing we have is the delta G of Cl2O, the delta G of formation for Cl2O. We don't have it for anything else, and we don't, therefore we can't do products minus reactants. So the only other equation that is available to us from what we've learned so far and based on the information given is the delta G equals negative RT ln of K, the Ratlink equation. So remember, the R we're going to be using is the 8.314, and that is in joules per Kelvin mole. Notice that in part A, it didn't ask us for delta G in any specific unit. So you don't have to give it in kilojoules per mole unless it specifically asks for it in kilojoules per mole. So we're just going to plug everything in. The R is going to be 8.314, the temperature is 291 Kelvin, and K is 0.090. So we plug everything in, and through the power of your calculator, you should get this answer, 5830 joules per mole. And remember, we predicted from up here that delta G was going to be positive since K is less than 1. And we can leave this in joules per mole, or you can convert it to kilojoules per mole. But again, unless it specifically asks for a certain unit, don't waste your time and risk making a mistake in a calculation that then you lose points on because you made a simple calculation error. All right, so that's, delta G of the reaction. So now we're going to find delta S of reaction. So let's think back to what we are given up here that will help us get to delta S of reaction. We can't do products minus reactants because we don't have the entropy value for HOCl. We only have it for our two reactants. So we can't do products minus reactants, the Big Mama equation, we can't use that. The only other equation available to us that involves delta S from the stuff we have is the going home to supper equation. We just found delta G in the previous problem. Remember, it's the 5830. So now we're going to plug that in for delta G. Delta H is given to us. This is one of those rare times when delta H is 0. It hardly ever happens, but it is. Okay, so delta H is 0. And we, obviously, you don't have to convert the 0 kilojoules per mole to joules per mole because it's still going to be 0. Temperature is 291, so we're going to plug everything in. And again, we can leave it in joules, we can leave delta G in joules per mole. Don't run the risk of making a mistake. So now we just need to use algebra to solve for delta S, and you should get negative 20.0 joules per Kelvin mole. And that's delta S of reaction. I was getting lazy and typing out all of the subscripts and stuff. Okay, so now we know we've solved A and B. And now we want to find delta HF and S for HOCl. So for that product that we don't have any information of, we're going to find those two things. Let's do the delta H first. So for both of these, we're going to be using, for both solving delta HF and S for HOCl, we're going to use the Big Mama equation. So for delta H, we're going to have to do products minus reactants of the delta H stuff. We know the delta H of reaction because that's 0 kilojoules per mole. We don't know the product because that's what we're solving for, and we know the information for both reactants. We have that here and here, and we're going to be using that. All right. So plug everything in. Now normally, in previous problems when we've been doing stuff like that, our x has been just a single x. There hasn't been a coefficient in front of it, but this time there is a 2 in front of it. So just make sure when you're doing the math, you don't forget to divide by 2 at the end. And that should give you negative 80.9 kilojoules per mole. So that's the delta HF for HOCl. And now we're going to do the same thing, but this time for the entropy for HOCl. We're going to use the entropy values for both of our reactants and the entropy value we found back here. That's the delta S for the whole reaction. So when I set this up, so again, products minus reactants, I'm going to plug in negative 20.0 for my delta S of reaction. That's what I found back here. And then again, 2x is on the left, minus, and then just, coefficients times these numbers. And this is going to be in joules per Kelvin mole, and you should get 218. All right, the next problem, or the next part of this problem, is finding the equilibrium constant at 300 Kelvin. So for this unit, the only formula we have that will help me find equilibrium constant is the RT ln of K equation, the Ratlink equation. Now the delta G that we're going to plug in here, you might think it's going to be the 5830, but it's not. Because remember, delta G is temperature dependent, the same as equilibrium constant. And this delta G here was for 291 Kelvin, not 300 Kelvin. So we actually have to do something first before we can find K for the reaction at 300 Kelvin. And the equation we're going to be using is the going home to supper equation. That's not what I wanted. There we go, the going home to supper equation. Okay, so we know the delta H, 0 kilojoules per mole. We know the delta S, negative 20. And we know the T, 300. Okay, so let's plug everything in. And this will be delta G at 300 Kelvin. And I'm not worrying about sig figs here. I'm just going to worry about them at the end. So, I mean, it's, or did I say 600? I meant 6,000. Whatever that number is. 6,000 joules per mole. This delta G, it's barely above the delta G we found before. But if you think about it, the temperature went from 291 Kelvin to 300 Kelvin. It wasn't a huge increase in our temperature. Going too far. Okay, so now we're going to plug this 600 joules per mole in for my delta G up here, and then I can solve for K. Just make sure you plug in 300 for your Kelvin. And I'm just going to leave this in joules per mole. When I solved it here, the reason I didn't convert it is because I knew that 8.314 was joules per Kelvin mole already. Remember, when you're doing this algebra, you need to isolate natural log of K first, and you should get negative 2.41. Now, our prediction, what sign does our delta G have? It's positive, so our equilibrium constant should be less than 1. So when to isolate to get rid of the natural log, we have to do e to both sides, and you should get a K value of 0.0902. Not much different than the original K value, but it is, getting a little bit larger. because we're becoming more positive. Okay? And that's it for number 9. Really straightforward, but just showing you different ways you can solve it. And the important part of this, or the point of all of this, was to show you that you might be given a whole bunch of information right at the beginning of the problem, but you can't use it all yet. So use the information that you're given and be able to identify what it is you need to solve. Like back here, delta G, we had to use the Ratlink equation because we had K. We didn't have enough of the other stuff to use any of our other formulas for delta G. Okay? Now for the next one. We have the enthalpy of combustion, delta H comb, or which is really just the delta H of reaction for oxalic acid. Okay, and that's C2H2O4. Sometimes it's written as like H2C2O4. I don't know why it was written that way this time. All right, and we're given that it's negative 246.05. So that's a very exothermic reaction, which makes sense because combustion reactions are exothermic. And then we're given a chart of all of these different informations, all these different substances, the delta HFs and the S values for all of them. All right, so for part A, we're going to write the balanced chemical equation that describes the combustion of 1 mole of oxalic acid. So oxalic acid is C2H2O4, and in a combustion reaction, we react that with oxygen gas. The products of combustion reactions with the hydrocarbon are CO2 and H2O. Okay? Now, when we balance this, normally, like back in first year chem, remember, for combustion reactions, you might have been told, oh, put a 2 in front of the hydrocarbon because you're most likely going to need it. But remember, this is asking for 1 mole of oxalic acid. So that means when we balance it, we're going to have a 1 in front of C2H2O4. And then in order to balance out the carbon, we're going to need to put a 2 in front of CO2. We're not going to want anything in front of H2O because we already have that'll balance out my hydrogen. And then we end up needing a 1/2 in front of O2. So it's going to look like this when it's balanced. All right, so just remember, fractional coefficients are a thing. So there's my balanced chemical equation. Yay. Now for this one, we're going to write the balanced chemical equation that describes the standard formation of oxalic acid. So standard formation, what that means, it's the equation that shows the formation, like the forming of that substance, and it's forming from its elements. So in oxalic acid, so the product is going to be oxalic acid of this reaction. And the elements that make it up are carbon, hydrogen, and oxygen. But we have to remember that oxygen and hydrogen are diatomic. So this reaction looks like this, unbalanced. So it'd be carbon plus hydrogen plus oxygen. And I got lazy and I didn't do states of matter, but carbon's a solid, hydrogen and oxygen are gases. Okay. So now when we balance this, just like with our combustion reaction, we wanted 1 mole of oxalic acid. Standard formation is for 1 mole of whatever substance you're forming. So when you balance this, you're going to leave a 1 in front of C2H2O4. And you would end up with this when you're balanced. You need a 2 in front of carbon and a 2 in front of O2. So now we're done with that problem, or with letter B of that problem. Now for letter C. We want to calculate the delta HF for oxalic acid. So let's think back to the 2 reactions we've written. We wrote this one, the C2H, the formation. I'm actually going to copy that over to this. I'm just going to put it right here. And we also wrote this equation. I forgot that wasn't a separate thing. Okay. All right, so we have these 2 reactions, and then we have a whole bunch of stuff. Oops. Messing up over here. Okay, we have a whole bunch of stuff in this chart, and then we have these 2 reactions. So let's talk through how we're going to figure out how we're going to solve for this. So we're trying to find basically this number right here. We don't know it. So let's think back to the things we're given. If we use this reaction, the formation of oxalic acid, the one I have in maroon here, the one I've highlighted right now, or selected. we would need to know the delta H for the entire reaction, and we know the delta HF of C, of H2, and O2. But we don't have the delta H of this entire reaction. Because guess what? The delta H for this reaction is the delta H of formation for oxalic acid, because that's what the reaction is. So this equation that we have here isn't actually going to help us in solving for delta HF of oxalic acid. So I'm going to delete that. Instead, we're going to be using this equation, the combustion reaction. Think back at the very beginning of the problem. We were told the delta H of combustion, or delta H of reaction, for oxalic acid is negative 246.05. And we also know the delta H of CO2, of H2O, and O2. We already knew O2 because it's always, it's elemental standard state, so it's 0. Okay, so we're going to do the Big Mama equation using delta H of reaction, and then equals delta H of formation of the products minus delta H of formation of the reactants. Delta H of reaction is the negative 246.05, and then we're just going to plug everything else in, which is going to look like this. Okay, we have 2 carbon dioxides, and that's negative 393.5. We have 1 water, which is negative 285.8, and then minus, oh, I just realized I typed that wrong. Oh no, you can see the answer. Okay, x plus 1/2 times 0. Honestly, that didn't matter because 1/2 of 0 is still 0, and x minus 0 is the same as x plus 0, but whatever, okay? So now we're going to, you already saw the answer, but you have to do algebra to find x, and you should get negative 827 kilojoules per mole, and that is the delta HF of oxalic acid. Okay. I have nothing else there. Okay, wonderful. So now we want to know the delta S of reaction for the combustion of 1 mole of oxalic acid. So to find this, we could, we have 2 formulas that uses delta S of reaction. We have the going home to supper equation, and we have the Big Mama equation. We can't use going home to supper because we don't know delta G yet. We haven't had to solve for that yet. Hint, hint, it's next. Okay, so instead we're going to use the Big Mama equation. We're going to do the products minus reactants, and we have all of the components we need here. Okay, but this specifically says the combustion of 1 mole of oxalic acid. So we will be using this equation here. Okay, we could find the delta S for this, but we don't need that. All right, so products minus reactants. We're finding delta S of reaction, so just plug everything in. These numbers I'm getting from the chart up here. Okay, for CO2 it's 213.6, for H2O it's 69.96, for oxalic acid it's 120.1, and then for oxygen gas it's 205. So you just plug everything in, multiply them by their coefficients, subtract the sum of the products minus the sum of the reactants, so on and so forth, and you should get 275 joules over Kelvin mole. And that's the delta delta S of reaction. All right. Now to find delta G, we're going to use the going home to supper equation. We have everything else. We found we were given delta H at the beginning of the problem. We just calculated delta S. We need temperature though. At no point has temperature been given, but remember this itty bitty degree sign right here means that we're at standard conditions. So unless the temperature is explicitly given, you can assume it's happening at 25 degrees Celsius, which is 298 Kelvin. So when you plug everything in, you also need to remember that your delta H and delta S need to be in the same unit. Okay, so right now delta H is in kilojoules per mole, delta S is joules per Kelvin mole. I converted my delta S into kilojoules per Kelvin mole, so I divided by 1,000. And you just plug everything in, and you should get negative 328 kilojoules per mole. And then the very last question is the combustion of oxalic acid at 25 degrees Celsius favorable? And the answer to that is yes. And the reason is because delta G is negative. And this reaction will actually always be favorable. And that is because the delta S is positive, so entropy is increasing, which is much more favorable. And the reaction is an exothermic reaction because delta H is negative, which is also, like, these are like the best case scenario conditions. A negative delta H and a positive delta S. That reaction will always be favorable no matter what the temperature is. All right, and that is